All right, hello, welcome back. So now let's analyze another question that we kind of went through in the first video. The question is, what really is the relation between a particle and a wave? This really concerns the idea of wave particle duality that you often study as being a confusing state of a particle being a wave and a particle at the same time. However, I want to stop that kind of talk right away in saying that particles like the electron, photon, let's say the neutrino, all these fundamental particles are just that. They are particles. No doubt about it. Any detector that we have made always has shown us by implementing a click click noise whenever particles get detected at the detector interface. So these are always going to be particles. However, we also see that the quantum behavior of these particles exhibits some wave-like phenomena like diffraction. So the only way we can explain it is by employing the fact that nature speaks in the language of mathematics. And it so turns out that there's a tool in mathematics that makes the explanation of the wave-like behavior of particles very easy and naturally implements quantization. And you would be amazed to find out, hopefully, that this mathematical tool that we employ to make our explanations easier is the concept of waves. Okay, so we can say that waves are just a convenient tool to explain the wave-like behavior of particles. So they're just a math tool. That's all that is. So these particles are never waves. They do exhibit wave-like behavior in a quantum sense. However, to explain that wave-like behavior, waves happen to be just an easy mathematical tool to do that. So what makes the wave interpretation so convenient? So that's our second question of this video. What is it that make waves a convenient tool in QM? It's just the fact that waves naturally quantize, right, physical properties. Let me give you an example. So I hope you have met standing waves or stationary waves in your basic physics course. And in a standing wave scenario, let's say you and your friend are having a bit of fun at the beach, and you stand here, your friend stands there, and you have in between you a rope that can make waveforms. So you both basically tug on the rope to make different waveforms. And let's say this is the average position. And the only waveforms that you can actually come up with is going to be either this simple waveform, or let's again have you standing here, have your friend standing there, this being the average position, or you can have this kind of a wave between you two. And since these are standing waves, the wave either reaches this way or it can also travel the opposite way back to you. And the same is true for here. Basically, the wave is restricted between you and your friend, so the waves just bounces back and forth, forming these kind of patterns. Or you can have, let's say, you again, your friend again. You can have, let's say, this kind of a wave. So no matter how hard you tug on the rope, no matter how you and your friend both give it a jerk every time it reaches you, essentially the waveforms can only be some specific shapes. So this is half a wavelength. So we identify this to be zero point 0.5 lambda. This is one full wavelength. So this is just lambda. And this is one and a half wavelength. So this is 1.5 lambda, right? So you can never have a 0.75 lambda, or you can never have 0.25 lambda, or you can never have 1.75 lambda. So these are what we call the vibrational modes of or frequency modes of the rope frequency modes. So these are the frequencies at which these the rope vibrates. So this is a very basic idea of quantization. So you can have specific numbers. They uh, and the numbers cannot be anything in between. Okay. So this is a quantized set of modes or quantized set of frequencies. So for example, you can never have a wave that looks like, so you have one full wave and then just that. Your friend stays there, you stay here, and you can never have this kind of a wave. This is not going to be true. Okay, the idea in quantum mechanics is also the same. When we hopefully go through the particle in a box situation in quantum mechanics, we will see that basically you have a box like that. You have a box and you confine, let's say, an electron here, or let's say any other particle. We ignore the spin for now, and the electron can go everywhere, but it has to go and remain within these walls. Okay, so it's a confinement of the electron. Okay, and if you solve the Schrodinger equation, the Schrodinger equation is the fundamental equation in quantum mechanics that explains uh, the the location or the probability of finding the particle at a particular point in space. If you go ahead and solve the Schrodinger equation, you will find that your solution are different waveforms that either look like that, or look like this, or look like that. So basically, the Schrodinger equation is a wave equation, and the solutions yield waves, unsurprisingly. And the waveforms are specific shapes, just like you have for standing waves between you and your friend. And there can never be something in between like that. Okay? And this concept basically extends into this idea for quantized energies of the hydrogen atom. So let's go and revisit this idea that we discussed in the previous video of the hydrogen energy levels being quantized. Okay, so quantization for the energy level means that, as we said, the electron can reside in the first energy level or the second energy level, but never some, let's say, one and a half energy level. That will never be true. So this is kind of analogous in to a situation of the electron being confined in a box. So you have the nucleus, this proton, you have the first energy level, you have the second energy level, and so on and so forth. And there's this electron. The electron if you give it enough energy, it can transition to a higher energy level and then drop back again. We have discussed this. And so we can say that, okay, the nucleus is, let's say, at position x equals 0. And let's say the first energy level is x equals L. The second energy level is x equals L2, and so on and so forth. Okay, so this can be like the box in which the electron is confined. The electron can be at x equals 0, but has to be confined between x equals L. So it can be anywhere in between these two walls. Or similarly, it can be confined in this wall from x equals 0 to x equals L2, and it can move out in between these two walls at whatever way it likes. Okay, so at any point, we are likely to find either the electron in between 0 and L, or the electron in between 0 and L2. And never will we ever find the electron in an intermediate kind of state. Okay, so the electron orbits, as Bohr would call them, correspond to electron orbits. Let's use an quotations, because orbits are not necessarily the correct term here. Electron orbits correspond to standing waves, meaning you can only have specific shapes, as we discussed for standing waves in classical physics. Okay, and the starting point is x equals 0, that's the nucleus, and the ending point is x equals L, L2, so on and so forth. Okay, so this is the energy level that it's currently at. Okay, and the endpoints must always coincide. So let's draw what we mean here. So you have the energy level. Let's say this is n equals 5. So n equals 5 means it will have kind of uh, 5, let's say 5 waveforms or something like that. So let's start here. So you have 1, you have 2, you have 3, you have 4, and you have 5. So it started here and it ended here. So the waveforms are attached at the endpoints. So this is a perfect or good solution for if we were to solve the Schrodinger equation for the hydrogen atom. This is a very hand wavy way in which I'm explaining it, just for proper visualization. Okay, so this is a legal solution. However, if you have, let's say, n equals 5 point, so 5 1 by 3, this is not a good state. As we know, the energy levels must be integers. So again, but let's just see what kind of a wave pattern it can form. 1, 2, 3, 4, 5. That this is not legal. You cannot be having this because the endpoints are not properly in sync with each other. Okay, so to conclude the video, we have seen that particles are just that, particles, lumpy things with definite mass, and waves are a convenient math tool to explain the quantum nature of particles. And hopefully, we have established the fact that quantization is only a consequence of the wave nature of particles.